Okay, last week, we studied how to evaluate a property of phase change material. So, when you have a phase change material such as water or refrigerant R134A, we can use a property diagram such as TV or PV diagram to determine the phase change process. And once you determine the phase change process, you can, follow this instruction to evaluate its property. Okay. So today we are going to use this table to study, to practice how to evaluate a property. So, completing this table is pretty straightforward. So each row represents a problem, an independent problem. So for example, if you look at the first row, we have a pressure and quality X. So based on these information available, we are going to determine its temperature, its specific enthalpy, and its phase. So that's what we are going to do. In the second problem, you have temperature and specific enthalpy, and you are going to determine pressure, quality X, and its phase, and so on. So let's look at the first row. In this first row, you can see we have pressure T, 200 kilopascal, and quality X. By the way, quality X is the ratio between saturated liquid and saturated vapor. So quality X is the ratio between saturated liquid and saturated vapor. So if you have 100% liquid, X is 0. If you have 100% vapor, X is 1. If you have X between 0 and 1, that means you have saturated mixture. By the way, X is the ratio between saturated liquid, saturated vapor. There is no quality X for superheated vapor or compressed liquid, okay? And if you look at this problem, it says that the quality X is 0.7, which is between 0 and 1. You can determine that the phase change process is going to be saturated mixture. So from this quality X, 0.7, you can say this is phase change process number 3, saturated mixture. If you have a saturated mixture, what is its temperature and pressure? Saturated mixture is here. So if you want to determine its temperature, it's going to be T set. And on this PV diagram, saturated mixture is here. So if you want to determine its pressure, it's going to be saturation pressure. Okay? So going back to this problem, is the pressure is 200. We want to determine the temperature of this saturated mixture. So the temperature is going to be the saturation temperature of at 200 kilopascal. Then if you want to determine the saturation temperature at 200 kilopascal, you need to find 200 kilopascal on a table. So it is 200 kilopascal. So you are going to, find this table A3, pressure table, because we know pressure. In this pressure table, pressure is the first column, and our is 200 kilopascal. The unit of this pressure is going to be bar. 1 bar is 100 kilopascal. So 200 kilopascal is 2 bar. So where is 2 bar? Right here. So T set is going to be, the saturation temperature is the second column, this one, 120.2. So this is the saturation temperature. then you can say temperature is the saturation temperature 120.2. What about specific enthalpy? Then you can go back to this summary slide. When you have a saturated mixture, how can you evaluate a property by using this linear interpolation equation? So where is H? This one. So let me write this equation. This one here. H is HF plus quality X times Hg minus HF. So where is HF? You can find HF at 200 kilopascal. HF is here. This one is HF. So let's find HF at 200 kilopascal. So this is HF. 504.7. 504.7. What about quality X? It's given 0.7. What about Hg? Hg is here. So let's find Hg at 200 kilopascal. This one 200. So we are looking at this one. 2706.7. So this is 2706.7. What about HF? We already found this one. It goes in here. So we have everything. Can you determine H? Yes, you can. So once you determine H from this equation, it goes in here. That's how you complete the first row in the table. Any question? No? Okay. In your first exam, you will see a table like this. Not exactly this one. I will change some numbers and also the properties. Instead of H, I may ask U or V. But you will see a table, which is 40% of your first exam. Then let's go to the second problem. Now this time we know the temperature. Temperature is 140 degrees Celsius, and H, the specific enthalpy, is 1800. So in this case, how can we evaluate its pressure and quality X and its phase? We need to make a property diagram. So how can you make a property diagram? Since we know temperature, there are two property diagrams. TV and PV. We can make PV diagram at 30 degrees Celsius if you know temperature. If you know pressure, we can make PV diagram. And as you know, we only know temperature, so we need to select the right-hand side, PV. And there are three pressure diagrams, PV, PU, pH. Among them, which one we are going to make? pH, because we know H, right? You can make PV, PU, no problem, but you know H. So it should be convenient to make pH diagram. So we can use this H. So let's make pH diagram. Looks like this. So pH diagram looks like this. At what condition? At 140 degrees Celsius. And pH diagram looks like this. This is pH diagram. So pH diagram looks like this. To complete this pH diagram, we need to know three property values. They are P set HF HG. Where can we find P set HF HG? From this temperature. So we go to table A2, temperature table. So this one is temperature table, where is 140 degrees Celsius. The first column is temperature, so let's find 140. This one here, so we found 140. The second column is pressure in bar, that is saturation pressure. So the saturation pressure is 3.613. So can I write 3.613 kilopascal? No, this one is bar. So if you convert it into kilopascal multiplied by 100, 361.3 kilopascal. 361.3 kilopascal. What about HF, HG? So there's a HF, there's a HG. So let's find HF, HG at 140. There is HF, there is HG. So let me write these two values here on this pH diagram. 589.13 kilojoule per kilogram, 2733.9 kilojoule per kilogram. Then on this pH diagram, we have compressed liquid, phase change process number 1, compressed liquid on this line, and this point represents saturated liquid, phase change process number 2, saturated liquid. This line represents number 3, saturated mixture. This point represents number 4, saturated vapor. And finally, this line represents number 5, superheated vapor. So that's how you make pH diagram. At this temperature. So we used this temperature to make this pH diagram. Now, we need to determine the phase change process. How can we do that? There are two property values that we know. One is 140, that's how we make this one. And the other one is 1800. So let's use this 1800 to locate our system on this line, okay? So where is H? 1800 is H. On this pH diagram, H is this horizontal axis. So where is 1800? HF is 589, HG is 2700. So 1800 should be between these two. So between these two, what is the phase change process? Yeah, saturated mixture. So this 1800 is between these two. So the only possible phase change process is going to be number 3, saturated mixture. So I can say here, phase change process number 3, saturated mixture. Then what do we need to determine? It's pressure. So this is our system here. Number 3, what is the pressure? This is pH diagram. There is a pressure, this vertical axis. So the pressure is going to be 361.3. 361.3. Then quality X. If you have saturated mixture, if you have a saturated mixture, we can use these linear interpolation equations, and we know H. So let's use this equation. H is HF plus quality X times HG minus HF. So let me write this equation here on the right-hand side. H is HF plus quality X times HG minus HF. So what is H? 1800. What is HF? 589.13. What is HG? 2733.9. What is HF? 589.13. So we have everything. Can you determine X? Yes. So what is this X? I don't know, but you can calculate that, right? Any question about the second problem? No? Yeah. So there is no surprise. It's very straightforward. Exactly, that we follow the instruction on the summary slide. If you have no question, let's move on. The third problem. By the way, is it too fast, too slow? I need some feedback. Good, or really fast? Yeah, I will, the slow down, like a slow motion. How slow? Next problem. No, not like that. My third class today. I'm so tired. The good thing is that there's no class tomorrow. Some people like to spread out their classes. I prefer put everything together. So straight one, the baseball game and over. So this is 9th inning. Okay, the next problem. Oh, the next nice problem. So this time we have pressure and quality X, right? So this time we have a pressure 950 kilopascal and quality X. And the quality X is 0. What does it mean? The quality X is 0. What does it mean? Saturated liquid. If you go back to this summary slide, the quality X is 0 only when you have saturated liquid. So I don't have to make another property diagrams. It is just saturated liquid. Phase change process number 2. Then what do we need to determine? Temperature. If you have a saturated liquid, which is this number 2, what is the temperature? Anything? No, saturation temperature. So we need to find saturation temperature at 950 kilopascal, right? So let's find T set at 950 kilopascal. And how convenient it is. There is a proper table. In reality, you have to, there are 96 pages of property table at the end of your textbook. I cannot give you the whole 996 page table because it's waste of resources, right? Let's save the trees. So I will provide a tables like this one, but not just the table. I will provide more than what you need. So let's say that you need 3 tables. I may give you 5 tables. So you need to select which table I have to use. Because if I give you the right table. How can I evaluate whether you can, find the right table or not, right? So if you need, if you need, let's say, the 5 tables, I may give you, the 7 or 8. So you will be able to, to find yours, but you don't have to find among, the 96 pages. Okay. And just for your information, in your exam, you can bring your own formula sheet, 1 page, letter size, so you don't have to memorize anything. This summary slide, you can write it down on your formula sheet and then bring it. You don't have to submit it because you want to keep it for the second exam, for the third exam. So after this semester, you can have 1 page, well made, only for you, unique formula sheet you can use when you go to your career. So you don't have to carry 1,000-page books. Whenever you have a question about thermodynamics, you don't have to go through this. You can just use this formula sheet. Some people I saw, that they even laminate it. So you can, that it doesn't go away, right? And you don't have to submit it. You can keep updating, but it's a letter size, not the size of this screen. Letter size, okay? About this size, front and back. It doesn't matter. You write it, handwrite, or the print doesn't matter. The font size doesn't matter. Anything you can write that help you to to solve thermodynamics problem. If you can even draw a cartoon, no problem. Okay. So let's find T set at 950 kilopascal. That means you need to go to which table? Pressure table, because you know pressure. So this is table A3, properties of saturated water. What table? Pressure table. And let's find 950 kilopascal. By the way, it's a kilopascal. The unit here is going to be bar. So 950 kilopascal is 9.5 bar. So let's find 9.5. 5, 6, 7, 8, 9. 9.5? No, 10. And what do we do? Keep up? No, you can do a linear interpolation, right? So let's do a linear interpolation. We want to find T set at 9.5. Zoom in. T set at 9.5. So T set should be here. So how can you find this value? Oh, maybe it's between these 2 numbers. So I'm going to randomly select maybe 177, 176. Can we do that? No, you need to do a linear interpolation equation. So this is how you determine T set at 9.5. The left-hand side is pressure. The right-hand side is T set. So what I'm going to write is the lower bound of each properties. So here, 9 and 10. 9 and 10. The corresponding T set values at each 9 and 10 should be written here. At 9, 175.4. At 9, 175.4. At 10, 179.9. Then what is the pressure of your system? 9.5. So you're going to write 9.5 where? Left or right? Doesn't matter. I'm going to write here, top left corner, 9.5. Then the unknown T set is going to be top left corner on the right-hand side, T set. What about the other, the blanks? Oh, this is time for promotion. So this 10 got promoted, 10 pay raise, right? No, not fun at all. Okay, 179.9. So if you solve this equation, you get T set at 9.5 bar. Okay? So if you do, it's going to be 177.65. 177.65. What about H? This is saturated liquid. If you have saturated liquid, how you determine H? H is going to be HF. H is going to be HF. So there is a HF. So what is HF at 9.5? This one, HF. So how can you find this HF? Again, another linear interpolation between 742 and 762. Between 742.83 and 762.81, and the top left corner, 9.5, here is the unknown HF minus this one got promoted, 762.81. So if you solve this equation, you get HF. It's going to be 752.82. Oh, doesn't matter. Doesn't matter. It's the same ratio. Yeah, you can solve this equation, or you can solve this equation, or you can solve this equation. They're all the same. Because we are calculating the ratio between these two. Ratio between these two. Ratio between these two. So they should be all the same. Okay? Any question about this third problem? The next problem, we have 80 degrees Celsius and 500 kilopascal. So now we have temperature and pressure, and we don't know the phase change process. So to determine the phase change process, we need to make a property diagram. There are two property diagrams, PV and PV. So which one do we have to make? If you know temperature and pressure. If you know pressure, you can make PV. If you have temperature, you can make PV. If you have both of them, which property diagram you need to make? Both. Doesn't matter. You can select one. So which one? This time, I'm going to select 80 degrees Celsius. So at 80 degrees Celsius, this one, I'm going to use this temperature to make PV diagram. I'm sorry, pH diagram. pH diagram at 80 degrees Celsius looks like this one, pH. This is the shape of the graph. So pH diagram looks like this. To complete this pH diagram, we need to know P set HF HG. Then where can we find P set HF HG? From this property table, table A2, temperature table. Why do we use temperature table rather than pressure table? Because this is the property that we know. Since we know the temperature, you go to the temperature table. If you know pressure, you go to the pressure table. To make this pH diagram, we need to know the temperature, so you go to temperature table. So let's find 80. Where is it? There is 80. So P sub is this one, and HF is, this is HF, HG. HF is this one, HG is this one. Okay, so I'm going to write these three properties to complete this pH diagram. So P sub is 0.4739. No, the unit of this pressure is going to be bar. So in kilopascal, it is 47.39. 47.39 kilopascal. And HF, 334.91 kilojoule per kilogram. HG, 2643.7 kilojoule per kilogram. So that's how you make pH diagram. On this pH diagram, this line represents number 1, saturated liquid. This point represents number 2, saturated liquid. This line represents number 3, saturated mixture. This point represents number 4, saturated vapor. This line represents number 6, 5, superheated vapor. So we made this pH diagram at 80 degrees Celsius. Now let's go back to the table. So we use this 80 degrees Celsius to make this pH diagram. Now it's time to locate our system on this pH diagram. So how can we do that? Using the other property that we know. So we know pressure. So where is pressure on this pH diagram? This vertical axis. So let's find 500 kilopascal on this axis. 500 is greater than 47. So P sub is 47. So 500 should be up here. So what is the phase change process? Yeah, number 1. So 500 is somewhere up here. So the only possible phase change process is number 1, compressed liquid. Then what is the quality X of compressed liquid? There is no quality X, because quality X is the ratio between saturated liquid and saturated vapor, and compressed liquid is not on the saturation. So this is not a saturation, right? So there's no quality X. Saturated liquid has quality X because it is at saturation. This one is not. So there's no quality X. So I have to say, oh, there's no quality X. No, you cannot leave it blank. You need to cross it out to show that there's no quality X. Then how can you determine specific enthalpy H? To determine specific enthalpy H, we have a compressed liquid. There are two options. One is when pressure is high, when the other pressure is low. What is the pressure of our system? Only 500 kilopascal, which is 0.5 megapascal. So pressure is low. And what we want to determine? H. So H is HF at T. H is HF at T. What T? 80 degrees Celsius. So where is HF at 80? HF, this one, at 80, 334.91. 334.91. Any question on this problem? Yes. Yes, we assume that the specific enthalpy of compressed liquid is the same as the specific enthalpy of saturated liquid at 80 degrees Celsius. If you know the pressure is greater than 2.5 megapascal, then you go to table A5. There's a table for compressed liquid. So the reason why we use this table, because when pressure is greater than 2.5 megapascal, the properties of compressed liquid is different from the properties of saturated liquid. So when pressure is high, yes, the high pressure affects the properties of compressed liquid, but when pressure is low, we assume that there is no effect from pressure. So we assume that they are the same. That's how we evaluate the property of compressed liquid. When the pressure is lower than 2.5 megapascal, the properties of compressed liquid is the same as the properties of saturated liquid at the same temperature. So that's why H of compressed liquid is HF, which is saturated liquid, as long as they have the same temperature. Any other question? No? OH. Yeah, I found it here. 752.82 after linear interpolation. If you see at the bottom here, there's HF. So you can solve this equation here and there, or these two. So either of them, you get the same answer. One more row in the table. Then it's over. And we can go to the next section, which is ideal gas. All right, so this is the last row in this table. This time we know the temperature, 1000 kilopascal. We know H, 3162. So what can we do? Do we know the phase change process? We do not know. So we need to make a property diagram. So what property diagram can we make? Pressure, temperature? Since we only know pressure, we can make TH diagram at this pressure. So when pressure is 1000 kilopascal, we can make TH diagram. Can we make pH diagram? You can't, because we do not know the temperature. We only know the pressure, so we can only make pH, not TH, because if you want to make pH diagram, you need to know the temperature. This time you know pressure, so you can only make TH diagram. And this TH diagram looks like this. So to complete this TH diagram, we need to know how many? 3 properties. They are T set, HF, HG. Then where can we find T set, HF, HG? From this pressure. So we need to go to pressure table. Here is the pressure table. What is the pressure? 1000 kilopascal in bar, 10 bar. So what is T set? 179.9. I'm going to write this value here. So there's a T set, this one, T set at 10 bar, and HF, HG. So we are looking at this number and this number. So these 3. So let me write these 3. on this table. So T set is 179.9 and HF is 762.81 kilojoule per kilogram. Hg is this number, 2778.1 kilojoule per kilogram. So on this TH diagram, here is number 1, this point number 2, this line number 3, this point number 4, this line number 6. No, 5, right? So we made this TH diagram at 1000 kilopascal. Now let's find where our system is. So what do we know? H is 3162.2. So let's find this value. So that H value, 3000. So this is H. So where is H on this TH diagram? This horizontal axis. So where is 3000? Greater than this number. Greater than this number. So this number is pretty high on the right-hand side, somewhere here. So what is the phase change process? Number 5, superheat vapor. Right? 3162, greater than this one, to the right. Greater than this one, to the right. See? Number 5, superheated vapor. Then what is the quality X of superheated vapor? There is no one, right? So you can cross it out. What is the temperature? So now we want to determine the temperature of saturated vapor. If we have saturated vapor, how do you find its property? Table A4. So let's go find table A4. So here is table A4. So here is table A4. Where is 1000 kilopascal? Here, 1 megapascal. So the properties that we are looking for is here. And H is 300,162. Where is H? This column, H. So let's find 3,162. 3,162 is between these two numbers, right? It's greater than this one, less than this one. So the temperature we are looking for is between these two numbers. So what are you going to do? Oh, we don't have the exact value, 3,162.2. So we give it, no, another linear interpolation. So the temperature we have is 3. So let's see. The left-hand side is temperature. The right-hand side is H. What is the lower bound? 320. Upper bound? 360. And the corresponding H values are 3,093.9, 3,178.9. And what is H value from the table? 3,162.2. Am I right? 3,160.2. So the temperature at this H is going to be here. That this is the unknown temperature. Then how can we complete this equation? 360, 3,178.9. So if you solve this equation, you get T. What is T? 350. So this is how you complete this table. And you will see a table like this with the different numbers and different properties in your first exam. Yeah. This one? This particular problem? Number 5, super vapor.
I'm saying, what if it's given?
If I give you, the phase description, you don't have to make property diagram because you already know the phase. Then you can just use this slide, right? If I, to give you the phase description, then you don't have to make a property diagram because you already know them. So if it is compressed liquid, follow this instruction. Saturated liquid, follow this instruction, and so on, right? But I doubt that I'm going to give you the phase description. I want to see whether you can determine the phase description, right? Oh, if you solve this equation, you will get approximately 350. 349 or 351, I don't remember, but close to 350. It depends. It depends. So that's actually a good question. So let's see. If you look at this problem, it is after you're solving this equation, right? So some people may get 34999, or some people get 351 point blah blah blah, or some people get 350. So which decimal you round up, you get different values, right? So any approximation is fine, unless you can say it's going to be 400 at the rounding up at 50, which doesn't make sense. It's too far, right? But if you look at the previous problem, this one, what is the saturation pressure? You get this saturation pressure directly from this table, right? So 361 at 3 kilopascal is the saturation pressure at 140. So the value is right here. What if you wrote, instead of 361.3, you wrote 361.2? Does it make sense? No, because the number is right here. So if you get 3.614 or 3.612, it doesn't make sense because you get this number directly from a table. So if you miss it, if you get the wrong value, any close value, that is incorrect. If the value is directly available from this table, then there is no partial credit. But if the value is after calculation, then any approximation is okay. And not about this particular problem, but in general, as long as there is a calculation, there could be partial credit. But to earn partial credit, you need to show your procedure, your solution. If you don't have any solution, just the final answer without any procedure, how can I evaluate how far whether you are in the right direction or not? So I need information to give you partial credit. So the more you provide in the solution, the more chance you get a partial credit. Okay? So if you think that, or you made a mistake, but you have no idea, write down as much as you know, so that that I can evaluate. Oh, this guy knows this much, so he deserves this much partial credit. So if there is no solution, but just final answer, the final answer, no matter what, regardless, the final answer is correct or not, if there is no solution, I cannot give you credit, right? So you need to write as much as you can. So you need to show how you follow, how you got this answer. Okay? The homework assignments and the problems in the in the classroom, they are very similar, in my opinion. So the bottom line is the same. Okay, as long as you have no difficulty solving the problems in the the PowerPoints and the homework assignments, I think there is no problem in your first exam. Okay. All right, let's move on. The next question and the next section is the ideal gas equation of a state. So previously we used, the proper tables because, our system may undergo phase change. But what if there is no phase change? What about the air in this classroom? Do you expect a phase change? No. Do you expect that, the oxygen and nitrogen here, they just become, the solid? No. If that's the case, we don't need to worry about phase change. We can evaluate their properties by a simple equation, and we are going to study a couple of equations. One is this ideal gas equation. The other one is called the specific heat, but we are going to study specific heat later. So let's talk about this ideal gas equation. This ideal gas equation is pretty simple, very simple. It is PV-RT. PV is RT. That means if you know pressure, if you know temperature, you can determine the specific volume. You don't have to determine the phase change process. You don't have to look for any table. You don't have to undergo any, the linear interpolation to evaluate this specific volume. You can get this specific volume directly from this equation when it behaves like an ideal gas. Then pressure has different units, specific volume and gas constant and temperature. So let's talk about that. If you don't want to worry about any unit conversion in your equation, always stick to these units. For pressure, kilopascal. For specific volume, cubic meters per kilogram. For gas constant R, that we are going to talk about that later, temperature should be in Kelvin. Okay, temperature should be in Kelvin. It's very important. Temperature should be in Kelvin. Don't forget that. Don't use degrees Celsius in this ideal gas equation. That's not enough. So I'm going to add, a few stars to show that this one is that important. Make sure that you use Kelvin when you use this ideal gas equation. Maybe 2 is enough. 3, 4, 5, and 6. Yeah, that I'm going to talk about that later. And this Kelvin is important, okay? Make sure that you use Kelvin when you use this ideal gas equation. No degrees Celsius. Then this R is called gas constant. This gas constant can be determined by this equation. R is R bar over M. This M is not lowercase m. It is called molecular weight. And this molecular weight can be found from this table, table A1. And this R is going to be gas constant, universal gas constant. It is always the same value, 8.314 kilojoule per kilomole Kelvin. And this M can be found from table A1. So if you have a gas, let's say oxygen, nitrogen, you can find the molecular weight of oxygen and nitrogen and use this equation to determine this gas constant. Just for your information, one of the most widely used gases in engineering technology is going to be air. So R of air, you may want to memorize it because we use this, the value a lot. It's going to be 0.287 kilojoule per kilogram Kelvin. Okay, that's how you use this PV-RT. Some people like to use, instead of PV-RT, you can also say P instead of specific volume V, capital volume V, which is actual volume. PV is MRT. Exactly the same because V is capital V divided by mass. Okay, that one was not that difficult. Now let's talk about, yeah, because this lowercase v is V over M. So this equation, they are the same, right? because this V is V over M. So if you replace this lowercase v with V over M, you get this equation. By the way, if you look at this equation here, TV is RT. Let's talk about each term one by one. Let's say that you have air as your system. Pressure of air, is it a variable or the constant? Air pressure. Air pressure should be always one constant or can be any number? One. So pressure of the air in this classroom is approximately 100 kilopascal. What about the pressure of the air on top of Mountain Everest? Different, right? So air pressure can be any number, 100, 200, or the 50, etc. So pressure is going to be variable. What about specific volume? It depends on the pressure and temperature, so it's variable. What about temperature? Air temperature should be always 20 degrees Celsius anywhere, even in dry sauna, or even the Antarctic, or the North Pole. We have a different temperatures, right? Inside the refrigerator, cooler than here, right? So this one is variable. Now the question: what about this gas constant? Is this gas constant a variable or a constant? That's a very silly question, right? Because the name is constant. The name is gas constant. So this R should be constant. Now we have a variable, 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 and constant. Why don't we move this variable to the left-hand side? By how? Dividing by temperature. Dividing by temperature. Then we get PV over T is constant. What does it mean? P1 V1 over T1. If you have air system, regardless of the what pressure, volume, and temperature they are, it is. If you calculate PV over T, should be always the same. Initial pressure, initial specific volume, initial temperature in this form should be the same as the final temperature, final volume, and final temperature. So there are two equations. This one and this one. These are the ideal gas equation of a state. So let's see how easy, how simple this equation is. What about if you have a rigid tank? So you have a rigid tank, there's air inside. I'm going to increase its pressure from 100 kilopascal to 200 kilopascal. But the temperature was initially, the 300 Kelvin. What is the final temperature? Sounds pretty, complicated, but it is not. If you use this ideal gas equation of a state, you can simply determine the final pressure. Let's see, a final temperature. It is a rigid container. So what happened to the mass and the volume of this air? Constant. It's a rigid container. The volume doesn't change. Mass doesn't change. So V1 and V2 should be the same. So you can cross them out. Now, initial temperature 300 and initial pressure 100. The final pressure 200. So what should be the final temperature? 600 Kelvin. So you don't have to, make a property diagram, determine the phase change process. Go find the property table. If you use this ideal gas equation, you can simply determine a property. So ideal gas equation is pretty simple and powerful because it's easy to use. However, there's one limitation. Real gases don't always behave as an ideal gas. They only behave as an ideal gas when their densities are low, which means when temperature is high or pressure is low, you can use this equation, but if temperature is low, pressure is high, you cannot use this ideal gas equation, okay? So that's everything about ideal gas equation. Any question? We have two problems. We are going to solve them together to see how we can use this equation. Let's look at the second problem first. Why? I don't know, maybe. So we have argon in the amount of 0.6 kilograms, and the volume is 0.05 cubic meters. So the mass is 0.6 kilograms. Volume V1 is 0.05 cubic meters, and pressure P1 is 550 kilopascal. And now piston is moving, and the volume becomes twice. So V1 times 2 is V2. So V2 is 0.1 cubic meters, and temperature T remains constant. So T1 is the same as T2. And what is the final pressure? And we can use the ideal gas equation of state, which is PV, T1 V1 over T1, yeah, is T2 V2 over T2. So in this equation, T1 is the same as T2, right? Temperature remained constant. Temperature maintained constant. So you can cross them out. V2 is 2 times V1. V2 is 2 times V1. So we can say 2 times V1. And V1 can be cancelled out. And P1 is 550 kilopascal. So what is P2? 275 kilopascal. Very simple. Because argon behaves like an ideal gas. So as long as you can assume that it behaves like an ideal gas, the problem becomes super easy. Even my 4-year-old boy can solve it. No, he can't. So any question about this one? It's pretty simple compared to the table, right? As long as you have an ideal gas. So the question is, can I assume this to be an ideal gas or not? So as long as you can approximate your system as an ideal gas, it's going to be pretty simple. Now the last problem, 10 minutes. Last problem. We have a rigid tank. That means volume is constant. So rigid tank. When you hear rigid container, that means volume is constant. The initial specific volume is the same as the final specific volume, and the initial temperature T1 is 1227 degrees Celsius, and pressure P1, that is gauge pressure, is 200 kilopascal, and there's a cooling process, so we don't know the temperature. We don't know the final temperature, but we know the initial the final pressure P2 gauge pressure is 50 kilopascal, when outside atmospheric pressure is 100 kilopascal. So what is the final temperature? Sounds like we can use the ideal gas equation of state. So let's do that. P1 V1 over T1 is P2 V2 over T2. Since it is the gas is in this rigid container, so you can assume that the volume is constant. V1 is the same as V2. Then what is the temperature? T1, 1227 degrees Celsius. What is P1? 200 kilopascal. And what is the final temperature pressure? 50 kilopascal. And can you determine the temperature at the final state? Yes or not? Is this correct or not? No, what is wrong here? Yes, you cannot use degree Celsius. You remember the 7 stars, right? So it's not 1,500 Kelvin. So if you solve this one, you get T2 or there is a mistake. When I say like that, there should be a mistake, right? It sounds like there's a mistake. So one mistake I made. Yeah, you cannot use the gauge pressure. You have to use the absolute pressure. So let's convert these to an absolute pressure. How can you do that? P absolute is P gauge plus P ATM. T anti-braking system is T automatic teller machine, right? No. Absolute pressure is gauge pressure plus atmospheric pressure. So gauge pressure is 200, atmospheric pressure is 100. So this is not 200, this is 300. The final pressure is not 50, it's 50 plus 100, 150. So if you solve it, T2 is 750 Kelvin. So this problem gives you the idea what pressure you have to use and what temperature unit you have to use. So up to here, we covered every material needed for your first exam. That means your first exam is a week from today, so you can have a week to prepare. Next Tuesday. Yes. Why? What happened? Oh, okay. I can give you a makeup exam. Okay. Send him an email so we can schedule a makeup exam. Okay. So let me give you a summary. Let me give you a simple study guide how you can prepare your first exam. So any question about the ideal gas equation? No? Good.